All right. Hi, guys. This is Mr. Crowfoot, and I'm here to talk to you about the Coriolis effect. And at this point, you should have done the warm up, which is right here. And if you haven't done the warm up yet, please take a moment, do that, pause the video, and then come back. So, for all of you that have done the warm up, though, let's go ahead and talk about it here. It says that you should think about the lesson on Hadley cells, which is to talk about uh, these guys right here. And for each location indicate the direction the wind would blowing on the surface. Okay, so like imagine that you're standing right here. What direction is the wind blowing, north or south, as a result of the Hadley cells there? So if you can't see it, I know it's a little bit, we're zoomed out a bit. Let's see if we can zoom in a little. All right, we can see that the wind would be blowing south right there, right? You can see this little arrow right there. So if you were standing, on the surface right there, the wind would be blowing to the south. So let's see here. So that's because, right, for 15 degrees, which would be halfway between 0 and 30, means you're right in there. That'd be going south, going south. If you're standing right here, right, then the wind would be blowing north. If you're standing at 45 degrees, so 45 degrees north would be right here. There you are. The wind is blowing to the north. And lastly, if you're down here at 45 degrees south, halfway between 30 and 65, just draw another little guy there, right, the wind would be going to the south. So there you go. So those are the answers to the warm-up, and looking at the Hadley cells, you can figure out what direction the wind would be going on the surface. So the next thing that we want to do is we want to take a look at, like, is that actually what happens? So when we look at the weather data, does the wind blow directly north or south at those locations? So let's toggle over and take a look at this map right here. And this map right here shows the wind directions at any given time. Or actually, I don't know when it's from, but these would be the general wind directions. And so you can see the little guys moving there, showing us the wind directions. And when we look at that, what we note is that we do not see winds going directly north and directly south, right? They have some east-west part as well. So if we take a look, here's our equator right here, this line. So our Hadley cells would be kind of in this region right here. We would expect them to be blowing south at 15 degrees. So they are blowing south, but they're also blowing to the west. And when we look down here, we would expect these to be blowing to the north. Given the warm-up we just completed, we expect them to be going north, and they are going north, but they're also going to the west. And so as we look at this data here, and just, right, it's not this particular area, by the way, like I can toggle over to here, and we see that very same pattern in this area, right? The wind is going to the north and to the west. So we would expect it to go to the north. The west is kind of interesting. Same thing right here. We would expect the wind is going to the south, and also to the west. We expect it to be going to the south. The west is kind of an interesting point on that. So why is that the case? So this east-west movement of the wind is caused by something called the Coriolis effect. So let's move over and take a look at a globe to better understand why that happens. All right, so here we go. Now we got our globe. And as we look at it, here's the equator right here. And our Earth is going to be spinning this direction. And so I've gone ahead and put two little pieces of paper on here so that I can draw on the globe. And so if we take a look at them, we know that in this area, right, between the equator and 30 degrees north, we know that the air is traveling to the south because of the Hadley cells, right, from our warm-up. So if I take a marker and I draw an arrow to the south, and I'm going to run my arrow straight up and down, so right, I'm just going to move it right along this little bar right here. And as I do so, I'm going to go ahead and turn the Earth as though it's spinning, just like it actually does, right? So here we go. I'm going to turn the Earth. And sorry, having some issues there, but right, we get that sort of a line. So as you take a look at that, right, you can see that we're getting kind of a curved line there. We'll go ahead and do the same thing with the southern hemisphere. Hang on, let me turn it around here, and all right, we'll draw the same line. Keep in mind that in this, right, in the bottom part down here, the air is traveling to the north. So I'm going to start down low down here, and I'm going to move my line straight up as I go, trying to turn it. And so, right, we see that we get a line, right, that is kind of up and to the left here. So, give me 1 second here. All right, so I went ahead and peeled them off the globe so that we could look at them here. And so let's remember that when I was drawing this for the southern hemisphere, remember that I was trying to mimic the Hadley cells, and the Hadley cells go north in the southern hemisphere. And so, right, I was trying to draw a line straight up, right? So what we see is that when I try to draw a line straight up, it gets curved to the left. Right there, you can see it gets curved to the left. So it was right because I moved my marker straight up, and the line ended up going up and to the left. So the northern hemisphere one is a little bit harder to understand, right? Because it looks like it's also going to the left. However, keep in mind that I was drawing my arrow straight down, as though something was moving straight down. So I actually have to flip this over to think about the direction that it goes. I was going in this direction, but then it curved and went that direction, so it actually curves to the right. So the Coriolis effect makes things in the northern hemisphere, right? The northern hemisphere, it makes them curved to the right, and it makes things in the southern hemisphere curve to the left. So hopefully that makes sense. Now, this particular way of kind of demonstrating this works really well if you have something that is traveling away from the poles towards the equator. So the demonstration that I did right there was able to show us this, and it works really well for thinking about how the Coriolis affects things that are going away from or going towards the poles. This same phenomenon, this left and the right, also works if you're going towards the poles, but the demonstration doesn't work in that case. So the demonstration only works to kind of initiate this right and left business. The right and left holds true for any motion, any straight line motion on the Earth. But the way of thinking about it doesn't work if you're going where we draw a line like that. It doesn't work if you're going towards the poles. That doesn't work. So anyway, thank you. Well, now we're going to head back to our assignment and fill a couple more things out. Thanks. All right.